Anybody remember what was different between Gaussian process and random process? Random process like f of t. Right here. Or x of t, maybe x of t. Or yeah, maybe I call y. So that was random process. And here we have, let's call it f, doesn't matter, f of t. And here we have f of x. They both function, okay? But what is the main difference between Gaussian process and general random process?
Follow a normal distribution.
What?
They follow a normal distribution.
Yeah, that's yes, that's correct. This is Gaussian. Yes.
Almost anything can index a Gaussian process.
Anything can be inside. X can be anything. Doesn't need to be time, but that's correct too. It's Gaussian, of course. It's Gaussian. So it means this function always have a Gaussian noise. If, for example, we have a y that we get some measurements, we have some sigma, that is sigma is following some Gaussian normal distribution like that, sigma I. So this relationship exists, that's Gaussian, but the main point is the x can be anything, even can be two-dimensional. It can be a space. That's why Gaussian process is so good for spatial modeling a spatial things, like, for example, geographical areas, for example, weather. You want to estimate those kind of things that related to two-dimension or three-dimension. But another thing about Gaussian process is we are extending distribution over function. Because x can be anything, any index, so we are kind of extending distribution over function. So it means if this is f of x, and if this is x, and this is the function, any function, we have distribution over this function. What is distribution? And it's Gaussian. So mean and covariance, that here we call it kernel. So this kernel showing how uncertain is this function. How uncertain is this function? Like how is varying. Like, for example, around this there is some variating. It's like a space that this function can vary, can change. And that's actually coming from kernel. This part coming from kernel. We talked about this last class. We said Gaussian process is important because kind of you can use it as a function approximation. You can approximate a function based of some observations. You can approximate a function. Function approximation, we also have function approximation in neural network. In neural network, we do function approximation. in, for example, dense neural network or deep neural network, we also do approximating a function. But in deep neural network, we break that down to neurons. Like, for example, each neuron do one of them. Like we get its input and we make lots of neurons and we make output. We do kind of same things, but in neural network, this is not efficient at all. We can see that today. In neural network, for each neuron, we call them neuron doing some linear things and some nonlinear, like it has some function like sigmoid function. You're going to see sigmoid function today as well. And we need to find these weights, for example, W and or maybe V and W, for example. V and W. We need to learn this weight. Anyway, neural network is also doing function approximation. Function approximation means what? Find this function. However, in neural network is all discrete, is not continuous. But in Gaussian process, this gives you exact function. It's a continuous function, and much efficient. In Gaussian process, you just need to have very simple training data to approximate that function. Very simple. Maybe for this, you just need 5, 6 number is enough. But for that neural network, you need thousands of data. Training data. When I'm talking about data, training data. What is the difference between training data and normal data? Anybody guess? I told last class. What training data means?
You need less data for the normal data than for training data? Or do you need the same amount?
No, there is something extra in training data. In training data, we have some extra things. We labeled them. They already labeled. Somebody labeled them. Training data is a data that is already labeled. What that means you know, for example, is correct or not. You know, for example, this data, for example, is object detection. You want to see if this is a chair or not. Somebody labeled them. So training data is a data that is labeled. So training data in this example is some data that is already around. It has some noise. Is around that real curve that we use those to fill it up, to do the rest. And that's called regression that we're going to talk today. So anyway, we're going to talk today about these things. We're going to talk about Gaussian process. We're going to talk about regression. Regression means how fill this. And we also can compare it with neural network. In other course, I was teaching neural network, and I asked a student to do one example, to do classification. And I did classification with Gaussian process as well, and we can compare that, how efficient is that. Okay, that's it. We want to talk about, also we want to talk about classification using Gaussian process. We can see that. Let's clean this up. So that's what we want to we talk. First, we start with regression. I think last class we started a little bit about regression, and then we couldn't finish it completely. So regression means finding a function based off some given data. So we want to predict a function like f of xi that based off this data, this function cover all of them. We have some sigma I2. So predicting a continuous function using some input data called regression. So you have some points, for example, you want to find is any function that passing all of this is called regression. Kind of we are filling all the gaps with a function. Why this give us? What this give us? It give us extra information. Between those gaps, we fill them. So it means if later, for this index, for example, we had this and this and this, for this xi, because we have the function, easily we can find the output. For example, this is yi. You just need to find this. That's the actually advantage of using regression. So regression gives us the function. So this function is valid for all of these indexes, all of these inputs, indexes or inputs. So this is called regression. It has lots of applications. For example, when for weather, want to estimate weather in some areas, we have some centers around the country, for example, that give us some samples of weather, but they are not everywhere. They are just distributed around. Like, for example, you have this is the map. You have one here, one here. This is all the centers that you have to give you data regarding weather. And but you want to find it somewhere else. It's called like xi. If it's 2D, is xi and yi, for example. Is x1, is it x2, and y2. So this is the map. x2 and y2, x3 and y3, x4 and y4, and x5 and y5. You have these centers. These centers give you some information about the weather, but you want to find weather, but your position is here, and you are driving, for example, in this area. You want to see what is the weather in this area. Oh, sorry. What happened? You want to find it here. There's no data over there, because this one gives you information around this. This one gives you around this. This one around this. There is a gap here, but you want to fill this gap. Gaussian process can fill that gap. How fill that gap? We want to find the f of x. F of x give us for all of these indexes. This indexes is x I, for example, and this is xj, for example. If give these 4 numbers to the 5 numbers to Gaussian process is going to fill everywhere for us. That's amazing. It gives us more than what we want. And it's very precise. The only thing that we need to be Gaussian. And for weather is Gaussian, of course, because weather is not changing dramatically, it's smoothly changing. That's why it's Gaussian. Anything that is smooth is Gaussian. Okay? Some stuff not Gaussian, but we can estimate them Gaussian. We can approximate them with Gaussian function. Okay, so that's regression. So definition of regression means predicting a continuous numerical value from some input data. Filling this up. We have some training data. Training data is like those centers, xi and yi, if it's one dimension, but they are noisy. They are not precise. But the noise assumed is Gaussian. That's the important part. We assume the noise is Gaussian. Even though they are true data or they are measurements and they are like samples, they are training data. If you look at that as a machine learning thing, they are training data, but training data is not also deterministic 100%. Is not. It has some variance, and that variance coming from the noise that measuring device has. If you measure the weather with some device, those device has some error inside. If we consider that noise Gaussian, we can find this function. So what is unknown is this function. So x is a random variable, y is a random variable. What is f of x? I. That's a latent variable. Remember, I talk about latent variable. Latent is not observed right away. You need to infer it. You do inference to get the f of x. So you do inference to get f of x. And in regression, we directly need to find f of x. So let's see what we can say about f of x. About f of x, first of all, is a latent function because is not directly known. We need to estimate it, or we need to predict it. We need to predict f of x. So is actually coming from inference. But what else we can we say f of x is Gaussian? Yes, that's Gaussian. Why? Because this noise is Gaussian. So then this f of x is actually a Gaussian process. Why is Gaussian process? Because it's a function. It's a function of x that has some uncertainty. So any function that follow Gaussian distribution and has some uncertainty, it means mean and covariance can be fit in a Gaussian process. So in Gaussian process, instead of having covariance, we have kernel. And last class, we talked about the kernel, and we said even the kernel is sometimes moving more than Gaussian. So you can have some type of kernel that are not really Gaussian, like they are linear or they are like periodic. And they can, that's why this Gaussian process makes lots of other applications. It's not just function approximation. But even function approximation is so amazing and so efficient and doesn't need lots of training data and doesn't have overfitting. One of the problems that mostly happening in learning from data or data-driven algorithms. Data-driven algorithms are the algorithms that you learn model based off data, like neural network, deep neural network, convolutional neural, any type of neural networks are based off data, but that data sometimes makes overfitting. Overfitting means you learn data too much. You even, instead of learning patterns around data, you learn even noise inside data. You learn the noise inside the training data. And for example, when you want to detect, like for example, you have a data that is in this shape, but it has some noise. Instead of finding the pattern that is, for example, ellipse or whatever, you can detect this neural network. If you don't do it good, it's going to learn this. Instead of learning the pattern, learning all the noise inside the training data. That's called overfitting. We can fix that in neural network, kind of. What I want to tell you, the Gaussian process doesn't have that. In Gaussian process, you don't need too much data. And it can detect patterns much efficient and smarter. Another problem in terms of function approximation compared to neural network, I don't know, are you guys know a neural network? Do you know? Okay, kind of. Do you? Okay. So you know. So as I said, neural network is also for function approximation. We are approximating a function using neurons. And do you remember function approximation? It was a law that neural network using that. What was that? Universal function approximation theorem, something like that. Universal function universal function approximation lemma. I don't know. There is a like a law that neural network working based off that. Based off that law, any function can approximate it using neural network just with two layers. Just with two layers. I mean, the one that I already draw. When I say in two layers, like this one layer and this is another layer. And they are just neurons. For example, there is some nonlinearity here. We have some, for example, V and W. So any function can be learned. So it means if you have some training data, it can find this function. However, it's not really function. Is function value is some values of that function because it's discrete, kind of discrete. Okay, because we are discrete this. Using these neurons, we are discreting this. Okay, why I wanted to mention that? Oh, I wanted to mention because here we have lots of extra things. We have lots of extra things, and it's not explainable. This is not explainable. When we detect something because of those nonlinearity that happening in these neurons, this makes it nonlinear. And we can't explain that, even though we have that rule, but it's not explainable. But Gaussian process is explainable. Is explainable. Why is explainable? Because it's based off Bayesian rule. We're going to see that. Okay, anyway, this is Gaussian process regression. We want to find f of x. We want to find this. And because we want to approximate it, that's the optimal one. And let's see how we can do that. And we have some training data that they have some Gaussian noise. And f of x is, we never observe f of x. That's why it's latent, is a latent variable. This f of x is actually latent function. We call it latent function. It's a latent function. Because we just see yi and xi, that training data, and we want to find it, f of x. Okay, so this is another thing that's coming. So yes, so the goal is to predict the function, and this function is actually, do you remember I told you best estimation or best prediction is conditional probability? That's a conditional probability too. So best prediction or best estimation is a conditional because it has everything there. When you are saying, when you want to estimate something like x, the probability of x given whatever, if you can find this, good, you can find x as well. How we can find x? You tell me. Imagine we have conditional probability of x given something. How we find x? That's called inference anyway. Inference. So we know probability that a robot be in this area is this much. So how we can find where is the robot? We need to maximize it. We need to get argmax. We need to get argmax of, we want to maximize this probability and find x, that this x maximize it. P of x, so maximize P of x given z. This is inference. We find x that maximize this probability. So we have this probability as a function. How we can find x? We just maximize it. That's it. That's called inference. And the rest is just linear algebra. Finding that x from this argmax is all linear algebra. It's very easy. Not easy, but it's already studied. Many people work on that. That's called inference. So inference means get x out of that probability. Okay, and here we want to find f of x out of this. That star that I put here, this is a notation that in Gaussian process use, but that means it's optimal. I mostly put that in top, but this notation is also means the unknown one. But because we are predicting that, it's f of a star. And we have x of a star and capital X and Y. Let's clean this up to see if you understand what they are. So what is this X star means? Let's go back to that example that we want to find all the space. We have 5 value. Okay. What is X? What is Y? What is X star? Any point? Any idea? First of all, what is X and Y? They are training data. How many training data we have there? 5. So this can be, for example, I don't know, 2, 3, whatever we have here, 3, 5, 3, and this is training data. What is X star? X star is all index here. For example, here is 100. It depends. You can make it continuous, but here you can consider 100 by 100. Can be 100 by 100 if you want to digitize it. But f of x is a continuous function. But here we just digitize it 100 by 100. So the x star is all the space. And f of that show all the values. So it means it's going to give you like this. Imagine it's like a random, what we call it, distance field. It's like a distance field. It's like a space. And we're going to show the picture. It's going to give you, with this x and y, these colors show you f of x1 and x2, for example. This is x2 and x1. F of that. So if we, it's like a 3D. What we show those intensity with colors, for example. But if you turn it back, you can see the hills. That those hills are f, the value of that function. So even though the x is 2-dimension, but the real picture is 3-dimension because we have another value, and what that value is f of x and x1 and x2, for example. Good. So the goal is to find f. And how we find it, we need to go for this. Let's clean this up. What is called? It's called posterior. I think we talk about posterior when we talk about Gauss, Kalman filter, I think, or when we talk about conditional, mean and conditional variance or covariance. Posterior means this. Posterior means probability of some unknown given some noun. We know the rest. We know x star. We know capital X. And we know, I don't know why we put capital X in this. That's just notation. Some notations just used for Gaussian process. But capital X means training data. And Y, and Y is also given. Y and X, capital X, are training data that coming from these values, I, Y, I, and Xi. And f star is something that we want to find. Latent function, we want to find latent function. And how we can find latent function, we need to assume something. We need to assume, we need to see if f star is Gaussian. That's the important part. Because if this is Gaussian, you can 100% summarize it with some mu and sigma. You just need to find mean and covariance or variance, and that's enough. So f needs to be Gaussian. In regression, f is Gaussian, 100%. Why? Because this y is Gaussian, has Gaussian noise. So that's why f of x is also Gaussian. based of that relationship. That's why this assumption gives us everything. We have another assumption here that assumption, or prior actually, is this K. We also imagine we know K. K is a prior information about the data. We know, okay, this data probably has, for example, exponential kernel, or this has linear kernel, though this system has actually the other one. I forgot. Okay, so that's another assumption. So that was regression. How we do inference? So inference means finding X out. So we want to find F. We know probability of F give off whatever. We can write this like that, or we can write probability of Y star given X star. However, they put a star down, but that's okay, and X and Y. These two are same. When we say F, we already have X star inside that. That's why we just put X and Y here instead of have 3 like the last. Okay, anyway, in regression, that's Gaussian. So if it's Gaussian, it has mu and sigma. So let's find mu and sigma. We also know about joint Gaussian. Do you remember joint Gaussian? This one? If you have joint Gaussian, X and Y are joint, we have some mean and a covariance. And that covariance and mean are actually very easy computable, not very easy, but computable. We knew that before in Kalman filter, in conditional mean and conditional covariance. We talked about that before. So the same thing's happening in Gaussian process, because Gaussian process is also like a vector of all of these random variables, that they are jointly Gaussian. Like this function is like these variables that are all jointly Gaussian. So we can kind of write similar thing with that. However, the covariance here is kernel. So we need to have 3 type of kernel. Instead of having sigma xx, we have kxx. Instead of sigma yy, we have kx star y star, x star x star. And instead of sigma yx, we have x star and capital X. Similar things, but different notations. And posterior, because here we also find posterior. This is posterior. This is posterior. Why is posterior? Because this mean of x given y is posterior. And sigma x given y. And this mu star is the same. Sigma f given x star and this and that. And we can compute mean and covariance for regression. These two are very similar if you look at them. However, this is around the mean. So because we consider here 0, for example, so that mean is disappeared, but the rest is very similar. So you can prove it that they are actually similar. So we have the function for mu and sigma. That's a function. And we know Gaussian process can completely explained by 2 values, mean and covariance. So we have all the function. That's why we have all of those functions. Let's see example. Here is example. We just have 5 variables, 5 training data. Is it very small? I can make it bigger. Like here, We have just 5 training data. It's one-dimensional. And we generate some data for y. Let's add some noise, because still we have noise. Even in training data, we have noise. And then we want to find the function. We already know the function. This is the function. But we want to kind of fill it using Gaussian process. So let's see how we can do that. So first of all, we have x and y. We have also some data, like we have sigma, because we are guessing that yi is equal to f of xi plus sigma. I don't know if this is the same sigma or not. Oh, yes, this is normal distribution between 0 and sigma. This sigma is this one. Okay. And so we make kernels. 3 kernel, kxs, x, kx, x star, and k star star. And the rest is just doing finding actually mu and covariance, because mu has k inverse. We find k inverse using this inverse function in Python. In MATLAB is also the same. Not the same, but similar things exist. So here we find inverse using this. This is exactly the function. This inverse coming from k. I don't know if I can write in this part. This is coming from k plus sigma n square I inverse. As you can see, it's exactly the same. So we do this part, invert it, multiply by k star, and the other one y to find mu, and for covariance also the same. So we have mu and covariance. And let's draw it. And the rest is just plotting. In plotting, you can see that it's gonna fill it up nicely. This is a true value, but because we add some noise, as you can see, these training data are very off. That's why what we feel that is not exactly similar to true data. We put too much noise. Maybe I should bring the noise down and try it again. But anyway, as you can see, this is distribution over function. Why is distribution? Because showing how this function vary, this gray area showing how this is vary. As you can see, this variance decreasing when it gets close to the training data. That's beautiful, isn't it? And this is very practical. We can see that in 2-dimensional as well, because this function, instead of having just x, you can have xi1 and xi2, 2-dimensional. But if you have 2-dimensional, let's go back to this. We had just 1 dimension here, but this picture becomes 2-dimension because of f of x. F of x add another dimension. And in 2-dimension, it's gonna get 3-dimension because f of x gonna add to that as well. Okay, so in this example, we have x1 and x2. So we are, the f of x is Gaussian. Why is Gaussian? Because we assume the noise of training data are Gaussian. We use this kernel, exponential family kernel, and we find mean and covariance same as the other one. Just here we have multivariant case, and the shape and the picture gonna be like a 3D, as you can see. We just have how many points? I think I don't know how many, but it's very little. I have the full picture here. 30. You just had 30 numbers, training data, these red dots, and the rest is all the function that the Gaussian process create for us. And you can see application of this. Amazing. You can use this for so many applications. I use that for detecting lane markings in the streets and give me very beautiful variance that, for example, which part, the part of the lane that wasn't visible, it increased the variance in that area, and it makes very beautiful continuous output. Okay, I think we couldn't finish it. Let's talk about classification next.